So in this video, we're going to discuss on the heat capacity, on the specific heat capacity. Okay, so as what we know that before, in order for heat to transfer from one body to another body, it required a difference in temperature. Okay, so we can illustrate this concept using a two beaker here. Okay, so if I were to have this water at the same height, then you will see that there's no net flow. Okay, but at the moment one side is lesser, then you will see that this water will flow to the right, and then eventually it will reach to equilibrium point. So this is similar to what we have discussed before. The temperature or the body reach a thermal equilibrium. So this is technically you can see about the same concept, as well as the flow. If we are seeing it to be like this, then obviously the flow of water can't in any way to flow in that direction in normal cases. Okay, so what does his heat capacity? So as what we know, this we can illustrate this level as temperature. Okay, so one side to have higher temperature than the other, and then you will see that the flows will goes there. Okay, so the amount of water here, so if I were to draw the same condition here but a little bit different. Okay, so if I were to have a difference in height as well here, then you will see a flow of water as well. But compare between these two, so it means that these two have a different in level of water. The same goes with the level of temperature, different in temperature. Okay, but what the difference between these two is that eventually both of them will reach an equilibrium point. Okay, equilibrium point, let's say going to be for this one is going to be like that. As for this one, it's going to be a little bit higher, like that. Okay, so if you look at here, the difference between these two is the height increase due to the flow on the left side of the container. Same goes here, but between the up and down example here, you will see that the top one increase more. Okay, it will increase more, whereas the decrement or decrement here is lesser compared to this one. So what I want to mention is that both of them have a different, significant difference in level, but one of them contribute less increment to the other container because of the quantity, the capacity. So what we are seeing here for the heat capacity, we can illustrate it or try to view it in the same way as what we're seeing right now. Okay, so one of them, the initial difference is the same, means that the initial temperature difference is also the same, but one object here have more capacity, so then it will produce more increase of temperature because it has more energy compared to this one. It has the same high temperature as the first example, but only that this material, this object, have less heat capacity. So although that the temperature has decreased, but the amount of energy received by the other object is less, and then the temperature increase is only slightly. Okay, so I think that could illustrate very well in terms of what we can understand about heat capacity. So in general, the equation of the heat capacity, or the definition of the heat capacity here, if you look at here, as what we have discussed just now, Q is actually the flow of energy, the amount of energy transferred from one object to another in order before it reach thermal equilibrium. Okay, so through that flowing of the heat going to flow continuously, endlessly, until the temperature of both of the object will reach a thermal equilibrium. Means that there's no different in temperature between the object and the surrounding. Okay, so then the heat transfer will be to be stopped. So that process, how much temperature has been reduced or changes through that process of heat transfer would be given by this. So okay, let's just go to example here. Okay, so then okay, before that the heat capacity here. So what mean by this? Whenever you heat up an object, okay, whenever you heat up an object, or liquid or object, doesn't matter. Okay, the amount of heat, let's say if I were to measure this, I provide the energy, let's say 400 kilojoules, and then it's increased, the temperature increased by say by 20 Kelvin. Okay, 20 Kelvin. Another one, okay, the same amount, the same amount of quantity, but in this case the same amount of quantity below, in that instead of 400 kilojoules, I provided 800 kilojoules. So then we're going to expect here the amount of increase in temperature would be double as well. It means that the temperature increase. So if it initially is 300 Kelvin, so then become 340 Kelvin, or for this one initially, let's say is 300 Kelvin, and then become 320 Kelvin at the final temperature. So what we see here, it is a proportionality of how much the object increase in temperature following to the amount of heat transfer. So it means that the more heat it receives, the more temperature it increase. So but this proportionality depends on the materials of the liquid or the object. So it means that if, as I mentioned before here, if the object have smaller capacity, so then it going to smaller capacity, so it means the same amount of energy here will increase more of the temperature, so it become hotter quickly lah. And so that's why we have metal to be can be heat up faster, so that it can heat up faster because of the heat capacity of the metal is very quite small compared to another more on the insulator side of the object lah. Okay, so the insulator technically have higher heat capacity, which cause it to hardly change any temperature whenever it been exposed or absorb heat. The amount of it absorb heat will have likely cause it to increase in temperature compared to metal, okay, which have lower heat capacity. Okay, but if you look at here, this heat capacity is also dependent, heat capacity also dependent on the amount. So it means that if I were to provided the same amount of so this example, so if I were to provide the same amount of energy, whereas the volume or the size of the material is being reduced to half, okay, you will see that the temperature also increase twice, okay, because the same amount of energy, only that the mass is or the quantity is being reduced to half. Then you will see that the previous the first example will only increase by 20 Kelvin, so the other one is increased for 40 Kelvin. So it is you can see that like that, if I were to have a bucket of water, or 5 liters of water, to heat up 5 liters of water here is much more difficult if I were to heat up only 100 milliliter of water. So yeah, something like that. Okay, this one will take more time because it require this one will take more time, as it required more energy to actually increase the temperature compared to this 100 milliliter of water. So if we consider to vary the same amount of material, let's say if I were to have an oil and water, the same amount of volume, we will see that the response of the amount of heat received by both oil and water will also be different. What I mean that if I were to provide both of these of 400 kilojoules, then I will realize that the oil will increase in temperature more quickly, higher in temperature, will increase more in temperature compared to water. So what do you think the causes of this? Which one will have higher heat capacity? Yes, the water will have higher heat capacity, and compared because of the water will have less temperature compared to the oil. So it's not that the amount of heat received by the oil is not received by the water is lesser. No, both of them receive the same amount of heat. It's only that the oil have lower heat capacity, cause it the temperature increase to be higher compared to the water. Although that both of these have the same amount of volume, and so this is not as what we have seen in the previous example here. The both of them have the same amount, but the material itself is different. So it means that the C, the heat capacity can be break into a mass and also a specific heat capacity. So we call it specific because it's specific to certain materials. So so the heat capacity depends not just the quantity of the object or the size of the object, but it also depends on the materials. So we can break down this equation Q equal to C del T. So this is only the heat capacity. We can break it into a more specific equation. So this is a capital C. This is capital C. Then we can break down into more specific categorization of values according to the materials. So then we have M del T, MC del T. Okay, so this is what we got, MC del T. Okay, so how to use this? How to use this? Let's go for one example. So if a metal of it's a 2 kilogram of metal of object required this. So this is actually Q of heat to raise the temperature from to 20 degrees Celsius. So this is initial temperature, so T, capital T, to 40 degrees. So this is final temperature. So what is the specific heat capacity? So the equation is Q equal to MC del T. So the Q is given, so the mass also been given. So Q is being given by like this, 10 power 3, and then mass is 2 kilogram. So the specific heat capacity is the one that we need to find. The change in temperature, so the change in temperature, remember that change is always going to be final minus initial. So here we're going to be 40 minus 20. So we arrange the equation, 10 power 3 divided by 2. So 40 minus 20 will left you with 20. So solve this, you should get this answer. Okay.